Wrong? Right? It's okay, all right. Good. Let's say, I'm tired of indices. So let's say AE1 plus AE0 plus BE1 plus CE2 plus DE3 is actually, minus a E sub 0 plus B E sub 1 plus C E sub 2 plus D E sub 3, which of course we could write in vector notation like this. That was the notation I was using up there. So there's something slightly interesting about the Minkowski raising and lowering indices, because if there's a 0 in there, you get a minus from the raising or lowering. All right? So let's see here. Oof. Starting to run out of energy. Let me show you guys. Well, fine. There's a way of thinking about the Hodge duality just in terms of kind of like, do you ever guys ever seen those like, you run into these sort of puzzles at like a county fair or something. It's like a snake with beans in it or something, and then like if you like squeeze it, the beans go to the other part, but like wherever you pinch down, the beans aren't. But like it's you know what I'm talking about? Or kind of like a tile puzzle where you move the tiles around. This has that feeling to me. So let me try to tell you what I'm talking about here. I'll get to the point eventually. So if I'm trying to calculate the Hodge dual of, say, E0. Oh, that's not a good one. Let's say E2. All right. Then what I do is I look at E1. Good grief. This zero convention is driving me nuts. E0, wedge E1, wedge E2, wedge E3. All right? And what you do is go, okay, well, that is, if I move the 2 over to here, I have to go 2 spots, right? So that's E2, wedge E0, wedge E1, wedge E3, right? Well, then, whatever's here, that will be the Hodge dual of E2. That's not, that would just literally be true if we were in Euclidean space. It's just that in Euclidean space. But because of the up-down index thing, I need like an extra rule for how it works with the possibility of the minus for the lowering of index. In my notes, I explain a careful like rule, which I don't have memorized, so I'll have to go look. I mean, we could just think through my general definition, but I'm not sure I have sufficient brain power for that at the moment. I also say to look at tables in my notes. I don't think the tables are there, though, so that's kind of mysterious. In old editions of my notes, I had tables of Hodge duals for the basic forms. So I'm trying to find I got an algorithm in here somewhere. If I can find it. I have like a step-by-step process if you don't want to think through my horrible definition, you know? Oh, here it is on page 161. I say start with the top form, E0, wedge E1, wedge E2, wedge E3. Permute factors as needed to place alpha to the left. So here's my alpha is e to the 2. All right. Permute factors as needed to place alpha to the left. I did that. The form which remains to the right will be the Hodge dual of alpha if no E0 is in alpha. Otherwise, the form to the right is multiplied by -1 is the Hodge dual. Okay, so since alpha has no E0, this is in fact correct according to my algorithm. If on the other hand I was, say, calculating the Hodge dual of E0 wedge E3, for example, all right? According to my algorithm, I start with the top form like this, all right? And so this is my, I'm calling this thing alpha, all right? I want to move that to the left. So E0 is already where it needs to be, and since I have to move 2 spots, I just get this, right? Do we understand? Are we all on the same page here? Because I had to switch 3 with 2 and then 3 with 1. Minus gives me plus. All right. So at this point, this is what's next. So this is my alpha, right? This is what's next to the alpha. Because there's a 0 in in the alpha, that tells me that the Hodge dual of alpha is actually equal to the Hodge dual of E0 wedge E3 is equal to minus E1 wedge E2. So there's a pesky minus that comes into play in the context of Minkowski space.
Alpha wedge dual of alpha is the
Oh, rats. Oh, alpha wedge, the Hodge dual of alpha is equal to definitely plus or minus the top form, right?
in this case.
That always has to happen because this is a P form and this is an N minus P form. So what you're left with is always going to be an N form, which in this context is always the 4 form. That's basically how the Hodge dual is, that's how the whole construction of the Hodge dual is achieved, is to use the fact that whatever's not taken up by your form in the top form, whatever's left over is N minus P, and that is the dual to it. Yeah.
And what about coefficients? Like in front of those?
It's linear, so if we understand Hodge duality on the basis, we extend linearly is all that happens. So yeah, everything, if we understand the basis, everything else falls right into line. So I have some more mappings I want to look at with you guys. Oh man. And then the break will begin with respect to this class. Let's see here. Oh man. So I do actually suffer through my tedious definition to calculate the Hodge duals in Euclidean space and Minkowski space. Like if you look at the notes, I actually have faced the music of my horrible combinatorial definition and sorted through some of these claims. So I won't go through the details much there. I'm just saying they're there to be seen. Hodge dual of E1. The components of E1 are Kronecker delta K1, all right, because we're in Euclidean space, so when you raise the indices, it's just that's the components of this dual vector. And, well, they're the contravariant components of that dual vector. And when you squash that all down, you just end up with ij, with this 1 being fixed. Since there's a 1 here, the only way this can be non-trivial is for these to either be 2, 3, or 3, 2, which is what I've got over here, which then the half and the fact that there's 2 gives you that, because this and that they're off by a minus in order to get, so this is -1, and that flipped gives you a -1. -1 gives you plus, so I got E23 wedge E23 twice. I mean, E2 wedge E3 twice, which gives me that. So, but that also you can achieve by the sort of just write it out and, you know, put the one you're trying to Hodge dual to the left, excuse me, to the left, and then whatever's to the right is the Hodge dual. In Euclidean space, that procedure works for the basis, and then you extend linearly. And as I was telling you guys, really, and perhaps I think very interestingly, the Hodge dual of the work form is the flux form. The Hodge dual of the flux form is the work form. That's very, I find that to be very interesting personally, but whatever. You don't have to agree with me. And you don't have to be so. Sometimes. So if you think through this, if I had not, let's see here. I think I wanted to think about a multi-index I. If I have a multi-index I and I move it out to the front, it costs me some sign factor, you know, whatever's left. And then -1 to the end, EJ is the Hodge dual of EI, multi-index EI. And then if I want to undo that, then it costs me the same sign factor to put I to the other side. So when you Hodge dual twice, you end up with -1 to the end and -1 to the end, which is 1. On the flip side, in Minkowski space, in Minkowski space, you got to be careful. This paragraph here, I assure you, is the result of like an hour of suffering, for sure. For me to write this here, like for 4 dimensions, we don't have cyclicity of the epsilon symbol. 0, 1, 2, 3 is minus this, is plus that, is minus that. So if I take the 0 and push it over here, I don't get a plus. I get a minus of what I started. So don't assume things work in 4 dimensions like they work in 3, especially when 0 is involved. Now, if it's involving just 1, 2, 3, then yeah, you've got that same cyclicity with respect to 1, 2, 3. But anyway, so after some suffering, I work out that the Hodge dual of E1 is minus E0 wedge E2 wedge E3. That seems to be opposite my rule I just told you guys, because there's no 0 in E1. Did I? Well, yeah, the minus is from the metric. I'm just saying what I told you over here is bogus.
What does E0 have to be in the alpha?
E0 has to be in the alpha. Is E0? Oh, E0 is not in the alpha. So I just kept the minus. Right. Yeah. Okay, thank you. So it is consistent with it's consistent with what I said earlier. If I could just remember what I said. The 0 is not in the alpha. Then I'm Hodge dualing E1. There's no 0 there. So I keep, well, this isn't the algorithm, right? But this is consistent with keeping the minus that you'd get from permuting the one, you know. E0, wedge E1, wedge E2, wedge E3. Yes, I'm saying wedgie. It's hilarious. All right, minus E1, wedge E0, wedge E2, wedge E3. I should bring my 11-year-old. We would have kindred spirits. Let's see here, but it's the same comedy stylings. It's very good, but yeah. So that's the Hodge dual of E1, right? And the minus, yeah, the minus also comes into play. All right. So, you know, that's what gave us the algorithm I described to you guys already. And so here's how it works out for like a 2 form. Same thing again. And this is really what I wanted to end with today, guys, is if we look at the Hodge, so like the work form map this is the flat of the vector, right? The flat of the vector v, we can get as minus e upper 0 wedged with the, I really do mean the flux form of the spatial part of the vector. So that's defined in the same way we did last time, like v1 with e2 wedge e3, v2 with e3 wedge e1, v3 with e1 wedge e2, like the same meaning here. And this one, the dual, this is a 2 form. I take the Hodge dual of it, I get another 2 form because we're in 4 dimensions, 4 minus 2 is 2. And so what I have here is I've got a 1 form, wedge another 1 form is a 2 form. So this is how the flux form and the flux form and the work form extended to 4 dimensions interact together with Hodge duality. Altogether, these are the rules, which these might be useful to us later when we're trying to solve a particular problem. I might give you like a, we can look at electromagnetism a little bit later, like Maxwell's equations, and we can use this algebra to like solve things there. So anyway, I think that's about it for now. So, if you'd like to see the definition of the upsilon map, you can ask Preston. I gave it to him earlier. So.